right, so, okay, hydration. See here, symmetrical and unsymmetrical. Hydrogenation, halogenation, symmetrical. Hydration and hydrohalogenation are unsymmetrical molecules. So let's take a look at water. There's hydrogen. There are slides here that go over what I just did. There's halogenation. Now let's look at water. It's got it right there, but let's say, let's use propene. Plus water. Now what I want you to envision water as, it's H2O, but think of it as this. That's H2O. That's H2O. But what am I concentrating on? I'm concentrating on one of the hydrogen-oxygen bonds and kind of, I'd say, ignoring the other one for right now because only one of these bonds is going to get involved. So let me erase that for a minute and just put it over here. I could have this situation, or I could have, there's two things that could happen here. I could have this situation. All right? It's still water, but there's two ways this water could approach that double bond. Could approach this way, and what am I going to get? Let me erase this here. Here's my water. What am I going to get in this case? This hydrogen is going to go on the end carbon. You see that? And this OH group is going to go on the middle carbon. So we would get something like this. We would get an OH right here. We would get a hydrogen right here. And the other hydrogens that were there to begin with, I'm just putting as lines. So you could see where that water came from. Where that hydrogen and that OH came from. It came from the water that reacted with the double bond. Or the water molecule could approach the propene this way, and the OH add to the end carbon, and the hydrogen add to the middle carbon. And I think you can see pretty clearly here that we would get a different product. I'm using propene because it wouldn't matter with ethane. It's going to go on the one carbon or on the other side. It's the same product each time. But with propene, it does matter. Let's name these. You can't name them because you haven't gotten into chapter 12 yet. That's right, you can't name these. So these are alcohols. When you hydrate, the hydration of an alkene produces an alcohol. So although we're in chapter 11, you're dipping your toe now into chapter 12 because this is one way of making an alcohol by the hydration of an alkene. But this is the OH is on the second carbon, the OH is on the first carbon, and you say, well, which product do you get? Well, you get some of each one of these, but one of them is the major product. This is the major product, and this is the minor product. All right? Now, there was someone in the probably late 1800s, I'm not exactly sure when he did this. The guy's name is Markovnikov. And you're going to want to remember his name because he established a way of predicting what would be the major product. I don't want to pour this on my camera. Got to be careful. He studied this. He hydrated. He did the hydration of a bunch of different alkenes. And he said, I don't get 50-50. I don't get half that and half that. I get about 85 to 90% of the product is that alcohol. And the minor one, 10%, this is what we mean by minor. The lesser alcohol produced is this one. The major alcohol produced is that one. So he did this over and over with different alkenes. And he came up with Markovnikov's rule. And what is Markovnikov's rule? Markovnikov, it's a simple rule. If you just kind of learn it. The hydrogen is going to add to the carbon with the most hydrogens to begin with. And the OH on the water goes to the other carbon. Now look at this. This carbon has 2 hydrogens. That carbon has only 1 hydrogen. So Markovnikov's rule says that for the major product, the hydrogen is going to go to that first carbon that has 2 hydrogens on it. And the OH is going to go on that carbon that has only 1 hydrogen on it. It's Markovnikov's rule.
How do you spell his name?
Right there. Markovnikov. Markovnikov's rule. He noticed that the majority of the hydrogen went to a specific end of the double bond. Let's see, does the next slide say Markovnikov's rule? Do I not have a slide that just tells me what that...
Slide 11.
Which is slide 11. Oh, the hydrogen of the acid most often goes to the end of the double bond, which had more hydrogens attached initially. Okay, now this rule is going to apply for hydration and also for hydrohalogenation. And what is the reactant here? HX. So it's either HF, HCl, HBr, or HI. That's hydrohalogenation. You can see here that for water, consider water this molecule. For water and for the hydrohalogens, the 2 halves of the molecule are not the same. So they're unsymmetrical reactants. A hydrogen is going to go on one thing, and the other part of this is going to go on the other carbon. So you can see how they're showing that water and HCl and HBr, HI, HF have a similarity here. They have a hydrogen and something else. So Markovnikov's rule applies for hydration and hydrohalogenation. Let's see here. Well, let me give you a little something to chew on. Complete this reaction. I'll give you the molecules. draw the major product. Of the hydration of this molecule here, which is 2-methyl-2-butene. What do you think will be the major product? Apply Markovnikov's rule. Okay, well, you know a hydrogen is going to go on one of these carbons, and an OH is going to go on the other carbon. You got a double bond here, so that water is going to add to that double bond. It's not going anywhere else. All right, so where is the hydrogen going to go? Is it going to go here or here? Here? This one. Right. Why? That's got a hydrogen. That has no hydrogens on it. That carbon has no hydrogens on it. 1, 2, 3, 4 bonds, all the carbons. So the major product is going to be where the hydrogen goes there and the OH goes there. All right? That's what we would predict based on what Markovnikov's rule has to say. And I mean, it's a rule, it's not a law. It works 95 or more % of the time. Markovnikov's rule guides you to predict the most common product, the major product. So, oh, I just did it again. Oh, you gotta be joking. Huh? I figured it out. I got it figured out. Relax. Okay. There's a little thing right there. It's a person. Okay. Okay, so that's the major product. Very good. All right, so there's some more. Here's hydrohalogenation. Since it's HBr, we would say this is hydrobromination. I mean, that would just be a little bit more specific word for it here, because we know the reactant is hydrogen bromide. It would be hydrobromination. But in general, it's hydrohalogenation. And let's see if, so we got propene here. So it's saying this hydrogen is going to go on this carbon. That's what you got here. This hydrogen going on this carbon, and the bromine going on the other carbon. We've got two hydrogens here. The hydrogen goes to the carbon with the most hydrogen, leaving the bromine to go on the other carbon. So that's your major product, your minor product. On your homework, I believe in cases like this, I say draw the major product for the reaction, So you don't necessarily have to draw both products. You need to draw me the major product. Figure out which would be the major. Don't worry about, okay, the hydration of alkynes. The only thing I would have you worry about with alkynes, but is just be aware of, let's imagine we had acetylene, which is ethine plus hydrogen. What is that going to form? Well, the very first step is you're going to get, I don't need this. You're going to get this. Okay? Can you see? If you started out with a triple bond and you hydrogenated a triple bond, one molecule of hydrogen would not saturate it. It would only take care of one of the double bonds. To saturate it, you'd have to react it with another molecule of hydrogen, and then you would get down to ethane. So you'll see me, the questions I ask you will concentrate on the reactions with alkenes, but I just want you to see that you can hydrogenate an alkyne. An alkyne takes two molecules of hydrogen to get to an alkane, to totally saturate it. Just one molecule of hydrogen will only eliminate one of the double bonds, or one of the bonds. So it takes a triple down to a double, then you need another hydrogen to take the double down to a single. All right? So very, very analogous reaction. You are adding hydrogen across a triple bond, but you're going to need twice as much hydrogen to saturate an alkyne as what it would take to saturate an alkene. Did I go over it? Or would I go over it?
Well, did you go over it?
Yeah,
For like an example?
I think I did, but maybe not. Here, we got one right here. There's one right there. So let's do that. We've got,
But that's halogenation, right? Not hydrohalogenation.
right, but what did you ask?
Hydro.
Hydrohalogenation? Okay. Okay, we got one right there. Okay? That's hydrochlorination, HCl. This is hydrohalogenation. Okay, Markovnikov's rule is going to come in here. Let's draw this in a way that we can see it a little bit better. We've got this carbon. We got okay, now, the major product. Tell me what would be the major product. We're reacting HCl with this. So where is the H going to go? Is it going to go on this carbon or this carbon? This one.
Yes. Yes, I see that one.
The hydrogen.
That one.
The hydrogen goes to the carbon that has the most hydrogen. See, there's a hydrogen here and a hydrogen here. This is Markovnikov's rule. This hydrogen is going to add to the carbon that has the most hydrogen to begin with. And the chlorine is going to go on the other carbon. So we're going to get this is the hydrogen from the HCl, and this is the Cl. All right, so there's hydrohalogenation. And this is the major product. Deborah, you see that? Okay. You know, the Markovnikov's rule, you have to kind of use it a couple times here till it becomes second nature. But hydrogen goes to the carbon with the most hydrogen. Doesn't matter whether it's HCl or whether it's HOH. whether it's water or a hydrohalogen. Okay, you can see here they're doing the hydrogenation using a nickel catalyst. That is a symmetrical reactant. Bromine, a symmetrical reactant. You just got to put a bromine on each carbon. You don't have to think about it as much. But when you get to water and a halogen, a hydrohalogen, you have to think about it. Is there a preference here? I think on the homework, this is one on the homework that might confuse you. I think I have a molecule, something like this. And it's reacting with, let's say it's reacting with HBr. And you go there and you go, what's your major and minor product? Can't figure it out from, it doesn't matter. Put a hydrogen on one of these and a bromine on the other one. There's only one hydrogen on each carbon. So you say doesn't seem to be any preference. So don't worry about it. Put a hydrogen on one of them and a bromine on the other one. But it has to end up with a bromine. You know, it has to end up with a bromine on one of those carbons that originally had the double bond. Bromine can't end up on the end. Bromine has to end up on one of these two carbons. Okay, I'm going to move along. All right, this is the answer to that previous slide. Working it out in line diagrams. Okay, another major reaction. So the first major category of alkene reactions is addition reactions, and there are 4 of them: hydrogen, halogen, water, and a hydrohalogen. The other major reaction of, come over here to my water bottle, is that alkenes are used to make plastics. Ziploc baggies are polyethylene. Ethylene is the common name of ethene. So the ethene is the IUPAC name, ethylene. Ethylene is this molecule we've been working with all day today. This is ethylene. All right, and so you take that and you polymerize it, and you can make polyethylene. If you were to take propene and polymerize it, you'd make polypropylene. Butene, polybutylene. You can make all different kinds of plastics, depending upon what monomer. This would be the monomer, the original individual unit that becomes polymerized. So this is a multi-trillion-dollar industry. If you run around the world, you're going to see a lot of plastic. Yeah. Cars, chairs, computers, plastic, the markers, the bottle, these bottles, it's all plastic. Polystyrene is used as a home insulation. It's all over the place. Plastics. So what they do down at Corpus Christi, they're taking crude oil, they get this black gunky stuff in, they shove it into these distillation columns, heat them up, and they're boiling out ethylene, purifying it, polymerizing it, and turning it into a beautiful clear plastic. All right? So they're distilling off these different monomers and making different kinds of plastics and other kinds of products out of them. All right, so how do they do this? If you were to take ethene, I'm going to draw a couple of these here. Remember, I've been telling you that these bonds, this is starting to look like an emoji of some sort. I'm going to just put the hydrogens up here. Why? I just want you to get a little feel for how this reaction proceeds. This is a very hot reaction. You could melt a reactor kettle if you weren't careful with how you did this reaction. What they'll do is they'll take something like this, just some kind of reactant. It might actually be something like this, a methoxy group. They do an initial reaction. They convert this into a radical, a free radical. Free radicals are highly reactive. And so what happens is this electron comes around. This radical bounces in here, and you get a bond here. And so this has an extra electron right here. So that electron moves up into this, and what you've produced is a free radical. You got an unpaired electron. It smashes into the next one, forms a bond right there, forms a radical there. This comes in here, forms a bond right there, and comes up there. And this just keeps, so you're polymerizing it. You're taking it from a monomer and converting it into a polymer. Many of these mers, many of these monomers, all linked together. So this goes on and on and on and on, and you end up, you got this thing right here. This is your repeating unit. Maybe there will be 1,000 of these, and then this little thing right here gets put on the end of it, and there's your big, huge polymer polyethylene. This is polymerization. Taking individual building blocks and turning them into polymers. Yeah, so here it is drawn out a little bit more pretty. There's your monomer, the catalyst, a little bit of heat and pressure, because this is a gas at room temperature, so you have to pump it on in as a gas. You got to control it because it's producing a lot of heat. You got to be careful. Rubber, they take this 2-methyl-1,3-butadiene and polymerize it, and you make rubber, like for automobiles, automobile rubber. There's your isoprene that we talked about earlier. Get it out of rubber trees. So it's a naturally occurring product. So what is this? This is nylon. Yeah, this is nylon. Let's not worry too much about that. Here's Teflon. How do you make Teflon? Well, you start out with tetrafluoroethene. Tetrafluoroethene. Replace all the hydrogens with fluorines. You polymerize it, and you get polytetrafluoroethylene, and it is Teflon. That's what Teflon is. All right, this is really worth paying attention to. If you take your water bottle, close it up real tight, turn it upside down, somewhere you should be able to find a little triangle. I'm not finding a triangle on this one.
Oh, it's right here. On the bottom.
Oh yeah, I see it.
Where's yours? Oh well, there should be a triangle. Oh, I see it. I see it. There it is.
Where?
Right there. if I get the water down in there, and it's got a 1 in the middle of it. 1. So what is that telling me? That's telling me this is polyethylene terephthalate. Polyethylene terephthalate. So it's polymerizing ethylene with terephthalic acid and making this is your repeating unit. 2 carbons, then the terephthalic acid, 2 more carbons, the terephthalic acid, 2 more carbons, terephthalic acid, that's polyethylene terephthalate. You see a lot of things, water bottles say no BPA, right? No bisphenol A. We don't typically you don't get bisphenol A out of this plastic. You get it out of this category right here, 7. All right, so the polycarbonates can leach out bisphenol A. Yeah, and bisphenol A is not good for you. It mimics a female hormone, estrogen or estradiol. I don't know what it can interfere, and the body gets confused as to what the bisphenol A is. It goes into the same receptors as some female hormones go into, and so it messes things up that way. So you want to stay away from bisphenol A. And then this is something they discovered 5, 6 or more years ago. I mean, the thing coming out, no BPA, that's fairly new, the last 4 or 5 years. Anybody remember that about 5 years ago they were concerned about it in babies' baby bottles? So because some of the baby bottles were being made out of polycarbonate and could leach out bisphenol A. Right, so that's good. But here, there are different kind of plastics. High density polyethylene for milk and water jugs. Low density polyethylene, sandwich bags. It's a little bit more flexible. Low density, it hasn't gotten as long. It's a smaller polymer. Polypropylene, polystyrene. There's your monomer, the styrene. All right. So they have different numbers, 1, 2, 3, 4, 5, 6 inside these little triangles. So you really shouldn't be warming food up and anything in a plastic that's labeled with 7. Better to do it in glass, actually, than to do it in that. All right, let me just, okay, we got a couple more things. Aromatics. Let's take a 5-minute break. We'll come back to aromatics, and then I'll let you finish your homework. something like around the triple bond is all straight. So cis and trans only applies to O. Yeah. Who's next? Yeah,
She sent me a snap.
well, I'd like a triple bond.
Thought about it though.
You start with a triple bond.
Do you? What does that mean? When we carry out the bottom line?
That's carbon number 2. So there's carbon number 1, 2, 3, 4. That's it. I'll do this for the whole class, all right?
Would that be okay too?
Let's see. Yeah, this one, that would be fine, but this one here could come straight out. All right? See what you did is you bent it up. Remember that triple bond is straight. Four carbons are all straight. Yeah, you're doing fine here, but you see the shape of that thing? Make this thing the same shape, so that carbon, you should go up to that carbon, not just straight out. Yeah, they can be like that. After that, it can be straight, right around the double bond. Be clear that one is coming in, the other one is going out, the same side, that one comes in. Says trans, comes in, goes across here, comes out, the other side is trans. No, around this double bond is the trans, not out here. Okay, so in other words, this carbon should come up here, and this carbon should come up there. All right? It's around the double bond that we see the cis or trans. Yeah, that's a tough one. Yeah, what I would do if I were you, I would draw the structural point here. And remember, find along the chain. What's the rules? You look at that carbon, what's the first question you ask? No, you ask, are there two different things that are in carbon? I have to take a quick break. You got,
This one.
yeah, that was like a little intake, yeah. That's good. You don't have to put a 1 or anything.
Yeah, and I like the hydrogen one. But
Okay,
I
yeah,
but I
I got
don't
it.
know which one. How do you know that one? Because you know how the
You should put it on here.
Did you write it like this? H-O-H or H-2-O?
Draw like this. Which question is asked now?
That's it's the same thing.
The same thing.
Right? Because I put 8. I put like that over here.
I'm not sure about the accuracy, but you see, like you draw like that. You said that it's okay. So it depends on you, right? We will ask something. Remind me. Okay.
No, I think this one's right because that's what I got too.
Hey, do we let you like try the name of the place?
No, I don't. It just says name the product form. I just did that because it so it wouldn't confuse me.
So what question is it asked for?
And then this
one?
that's what yeah. And then this one. So you just name it. Okay, how did you?
No. So cyclopentate it looks like this, right? So do you remember when it's what to try?
Then you just add an iodine.
For example, it's look like wait, how do you no, it's up to you. Like you can put 1 or 2 because it's a cycle. So it doesn't matter about the number. So I'm gonna change it. It's not true.
Well,
You can put 1.
ask, look at those carbons. Ask yourself.
It's just that weird name.
Three questions. Yeah.
I'm gonna put this, the IO, IO.
It's like this.
So it's neither. So then use the IUPAC rule. Find the longest chain. Find the longest
And
chain.
pentanase 5.
Name the chain and then
IO cycle.
constituents that are left over. There aren't in the name. Okay, let's cover aromatics, and then I'll make another comment or two. I think let's see, which one was I gonna draw for you guys? Number 1. We'll draw number 1 in a minute, and then I'll give you a few minutes to finish up your homework. But let's understand what aromatics are. Okay, now we've got double bonds here, but we've got alternating double bonds in a ring. You can see a double, single, double, single, double, single bond going around in a ring. You'll hear me use the word conjugated double bonds. It's just, I think, a fancy word for alternating double bonds. Aromatic. There were molecules like this that kind of had different aromas, different fragrances, aromaticity. So they said, well, these are aromatic compounds. So they got to be referred to as aromatics. The simplest one, the main one you're going to see over and over again, is benzene. 6-membered ring. This is benzene. This is your poster child. This is a carcinogen, by the way. Benzene is carcinogenic. Where would you find it? Well, you could find it in probably automobile tires. So don't suck on automobile tires. Might be a little benzene in there. Now notice, look at each one of these carbons. I've got 1, 2, 3 bonds around there, so there's only 1 hydrogen there. I'm going to go down to the next one. 1, 2, 3 bonds, there's only 1 hydrogen there. Next carbon, 1, 2, 3 bonds, 1 hydrogen. 3 bonds, 1 hydrogen. All right, each one of these only has 1 hydrogen on it. So the formula here is C6H6. That's the chemical formula of benzene. We do not technically call this an alkene. It is an aromatic. Even though there are these double bonds in there, you cannot hydrogenate this the way you would hydrogenate propene or hexene or cyclohexene. They'll react the way I was explaining earlier. The hydrogens will add across it. But these are particularly stable rings, and they react even differently than alkenes do. All right, so the German chemist Kekulé studied this extensively, what's going on here. It isn't really that there are 3 distinct double bonds and 3 distinct single bonds. It's more like the bonding is just kind of dispersed around in there, and so you're going to see this for benzene as a line diagram, or this. These are identical. Or this. Doesn't matter where I put these double bonds, just as long as they're alternating. So all of those are equivalent drawings for benzene. This one here is probably the most common, what you'll see the most, because it's easiest to draw. You draw a 6-membered ring and just draw a circle on it. And you're saying what we're talking about here is an aromatic. There's slides here that go into a little detail what Kekulé found out. Yeah, this is what I just drew over there. 2 equivalent drawings of it. The double bonds are in different positions. We call those resonance structures. 2 drawings you can make that are equivalent. Yeah, Kekulé is the one that said what you really have. This is kind of describing the electrons. There's this kind of a cloud of electrons above and below the ring. A pi cloud of electrons gives it a particular stability. I don't expect you to go into that much detail on this. There's overlapping orbitals. If you got into what are the molecular orbitals in a benzene molecule, this would be of interest. All right, the different drawings of it. Again, it's flat. If we made a molecule, if we put this all together, what you would actually find, unlike the cyclohexane where hydrogens are kind of coming out, everything would be in a plane. It's a flat molecule. The hydrogens are actually sticking straight out from the carbons, and it'd be a flat, planar kind of a structure. Okay, some nomenclature. So benzene, I told you benzene was the major molecule. There's chlorobenzene, nitrobenzene, ethylbenzene. What is the one you need to? Okay, this one you should make you should have a 3x5 card for benzene and a 3x5 card for toluene. Toluene. This is benzene with a methyl group on it. So benzene is the IUPAC name and the common name. It was called benzene when IUPAC came into being, and they said, we're just going to adopt that name as its official name. So, and toluene, I guess you could call it methylbenzene, but it's most often called toluene. You're going to eventually learn these other molecules, but you're going to learn this one in chapter 12. You're going to learn this one in chapter 14. You're going to learn this one in chapter 15. So I wouldn't worry about memorizing these structures yet. They'll come later, but don't get yourself too confused before exam 1. Just get benzene and toluene on 3x5 cards. All right?
We just have to draw them, right? Or what do we have to know about?
Just draw them. Yeah, if I said draw benzene, you could draw it. Or if I gave you the molecule or gave you a drawing of the molecule, you'd be able to name it. You need to go both ways. Go from the name to the drawing, drawing to the name. Okay, now we've learned substituents, methyl, ethyl, propyl, isopropyl. Now you need to learn phenyl. Phenyl. So if you, let me draw this molecule here. Let me straighten this out. What is that? 1, 2, 3, 4, 5 carbons long. I'm just straightening that molecule out. Here's carbon number 3. Right over here, we've got this substituent. So what is that? That is a phenyl group. Remember, you're seeing the YL ending on things that we call substituents. And so how would we handle benzene if it was a substituent on a organic molecule? This is how we would handle it. We would refer to it as a phenyl group. And it's on the 4th carbon. This is carbon number 1, 2, 3, 4, 5. So that's 4-phenyl 1-pentene. Okay, so now that's another 3x5 card. What is a phenyl? Here's your 3x5 card. Here's the other side of it. This line, this last line I put on there, is where it's attaching to a carbon of a molecule, an organic molecule, wherever it happens to be attached. In chapter 12, you're going to be introduced to a molecule called phenol. We just looked at it right there. There's phenol. So don't get phenol confused with phenyl. Okay? Phenol is a compound. It's a benzene ring with an OH group on it. Phenol is a substituent that is hanging off the side of a organic molecule. You see the distinction? All right, you'll get it as you work with it. Yes?
So, which is which, because you put
Phenyl with a YL is a substituent. Phenol with an OL is the alcohol, the aromatic alcohol. Phenol. OL, we haven't gotten to chapter 12 yet, but molecules ending with an OL are alcohols. Things ending in YL are typically substituents. Isopropyl ends with a YL. Propyl. Ethyl. Okay? Okay, just another term to just kind of be familiar with. You've heard it, you're hearing it now. Heterocyclic aromatics. Benzene is a homocyclic aromatic. All the atoms in the ring are carbons. But heterocyclic, and usually it is carbon and nitrogen, particularly in really chemistry of interest. Sometimes there'll be an oxygen in there, but something other than a carbon means heterocyclic. It's a mixture of elements in the ring. So pyrimidine, purine. We will look at these in chapter 20 when we get to DNA and RNA. You'll see these heterocyclic rings. You don't have to memorize these structures now, or I don't even think in chapter 20, okay? But when you hear the term heterocyclic, that's what we're talking about. Okay, here's this is the one reaction of aromatics that I expect you, so in chapter, well, we'll summarize all the reactions in chapter 11 in just a second. But this is one of them, the halogenation of an aromatic. Like I said, it doesn't react like alkenes. It's not addition. This is a substitution. If we take benzene, react it with chlorine, with this catalyst iron chloride, one chlorine goes on the benzene ring and replaces a hydrogen. The hydrogen comes off and replaces the chlorine. All right, so benzene plus chlorine, you get chlorobenzene and you get HCl. You're not adding, and you haven't eliminated a double bond. It's still benzene. It's now chlorobenzene. You've added a chlorine on there, but not two chlorines, just one. Follow me? So that's the essence of the halogenation of an aromatic. So, be able to handle fluorine, bromine, iodine, would all do the comparable thing here. You would get one fluorine on benzene and you get HF as the other product. I think, okay, now we're just looking at the summary of reactions. Summary of reactions, here's the symmetrical, unsymmetrical addition reactions to alkenes. All right, there's just another list. Markovnikov's rule is applying to hydration and hydrohalogenation. I don't know why these aren't kind of listed that way. And these here are symmetrical. Polymerization. Halogenation of benzene. Those are probably the three main categories of reactions from chapter 11. Is that the last slide?
Yes.
Okay. All right, take a few minutes and finish your homework. Oh, I said I would do number one. Let's do number one. What's the name of the molecule? What is it?
2-hexyne.
One,
2
two hexyne?
with a Y.
Okay, 2-hexyne. All right, so let's do the 5, 6, and on the second, starting on the second carbon is a triple bond. All right, now if I look at this, this has one bond, so I hydrogens here. I look at this carbon. 1, 2, 3, 4 bonds. What goes on here?
No,
Nothing. 1, 2, 3, 4 bonds. What goes on here?
nothing.
Nothing. 1, 2. So this needs 2 hydrogens. 1, 2. So this needs 2 hydrogens. And 1, 2, 3, 4. So there's the, just doing this, I want to go to the line diagram so you just kind of see how to do this. If I'm doing a line diagram, and when I showed you the models, I said around the triple bond, these are 180 degree bond angles here. So what does that mean? This, and this are in a straight line. These 4 carbons are in a straight line. So what you can do here, there's your triple bond, starting at the second carbon. There's your first carbon, your second carbon, your third carbon, your fourth carbon. They're all in a straight line. Fifth carbon, sixth carbon. All right, so around a triple bond, I don't care what it is, you can have 4 things in a straight line, and then bend from there.
But with the double bonds, we can go.
With the double bonds, you have to go at an angle. Remember, I'm saying that around the double bond should look like this. This is what it should look like around the double bond. I wouldn't particularly like to see it looking like that. And you put hydrogens up here. This here, then you get into cis and trans. Cis says, okay, I'm going to have something here, and it's going to come out there. And if it is cis, then in a line diagram, it's going to look like that. Now, some of you may have it looking like this. That's fine. That's still coming out of the same side of the double bond. That cis and trans should look like that. All right? Not, and even trans then would look like this. Maybe a hydrogen here or something. But you can see the basic arrangement that I'm saying around a double bond should be like this. And around a triple bond should be like that. That's what it should look like around a triple bond. That's what it should look like around a double bond. You just have to figure out what goes around there, but that's the geometry around the double bond. Okay, when you're done, just bring your chapter 11 homework up here, and we will start chapter 12.
Can this be like this, or does it have to be flat? Or can double bonds be up and down?
Yeah, they can be up and down. They don't have to be flat. That's fine.
Okay.
Yeah, and you got a bend there. That's fine.